All right, so we've got a regenerative cold air standard Brayton cycle. We're given a volumetric flow rate, we're given the pressure, we're given the temperature at the inlet. We're also given some isentropic efficiencies and a regenerator effectiveness, and we're told that the maximum temperature is 2100 Kelvin. And that would be after the combustion process. So that's where that's modeled from state 3 to 4 as a heat addition process. So you've got heat addition from state 3 to 4, you've got heat rejection from state 6 to state 1, and then you've got some regenerated heat between 5 from the process of 5 to 6 to 2 to 3, but that Q regen is not taken into account when calculating your thermal efficiency. All right, so we're making cold air standard assumptions with the exception of the fact that we have an isentropic efficiency, and we've also got a regenerator effectiveness of less than 1, and then my other assumptions are listed there as well. So I'm going to go ahead and get my roadmap of where I'm going, get my governing equation. So the work net out, it's going to be the work of the turbine minus the work of the compressor, and the heat in. This is going to be between states 3 and 4 where we're modeling that combustion process. Or I could put this in terms of 1 minus Q out over Q in, and the Q out is not drawn on the diagram here, but it is understood to occur between state 6 and 1. So that's where the exhaust process happens, but we're modeling it as a constant pressure heat rejection process. And then our power output, well, I've already calculated what the work output is, or have an equation with that. So it's the work of the turbine minus the work of the compressor. And then you need to multiply it by the mass flow rate to get it in the units that you want. You need it in kilowatts or megawatts, I guess. And then our mass flow rate, the way that you're going to calculate that is from the volumetric flow rate at state 1. So the mass flow rate should be the same at state 1, state 2, state 3, state 4, state 5, state 6, because it's just one continuous loop. So I'm going to calculate the mass flow rate at state 1 given those parameters, and I'm modeling air as an ideal gas, so I can use the ideal gas law to calculate the specific volume, which is the denominator in this equation. Okay. So now let's start plugging in numbers or calculating our states. So state 1, that's given, it's 280 Kelvin. State 2, well, we're given an isentropic efficiency, so we need to figure out what state 2 is at the end of an isentropic process. And for that, we're going to use an isentropic relationship. So I know P2 over P1, I know K is equal to 1.4, and if I just do the math, I get 658.99 Kelvin. For state 2, I'm going to use my isentropic efficiency equation. So it's the isentropic work over the actual work. And the actual non-isentropic work is on the bottom. So T2 is 691.95 Kelvin. And now we're ready for state 3. So the way that I'm going to calculate state 3 is by using my regenerator effectiveness equation. So it looks like I know everything in that equation except for state 5. So I'm going to come back to it. I'm just going to put a pin in it. State 4, that's given. It's 2100 Kelvin. That was the maximum temperature within my cycle. State 5, well, this is after a non-isentropic expansion process within my turbine. I do need to calculate state 5s, so the state at the end of the isentropic expansion within that turbine. And because I know P5 and P1 are equal to one another and P4 and P2 are equal to one another, I can calculate T5s. So I've got 892.27 Kelvin. And then I can use my isentropic efficiency of that turbine to calculate what state 5 is at the end of the non-isentropic process. So 252.66 Kelvin. All right, let's see. All right, let's keep on going. So we've got state 5. We can plug in, we can plug in the numbers at state 3. Now that we have state 5, we can calculate what T3 is, so 913.55 Kelvin. And if we really want to, we can calculate state 6 based off of the regenerator effectiveness. So it's the maximum heat transferred from maximum heat transferred by regeneration. And if we look at things from the point of view of that little segment from 5 to 6, The actual heat regenerated is Cp times T5 minus T6 minus T5. And the denominator, the maximum amount of heat transferred, would be the heat transferred by regeneration if by the time that air flowed from state 5 to state 6, it would have cooled all the way down to state 2. Ideally, T6 would be equal to T2. So that's where our denominator comes from. So I can calculate a temperature T6 of 731.06. And once again, it's not really necessary to calculate T6 based on our governing equations here, but you can go ahead and just check and see if your logic is sound to see if your work net out is equal to your Q net in. And then if I plug things in, you'll get a 62% thermal efficiency and 44.145 megawatt for your net power output. All right, thank you very much for watching. Let me know if you have any questions.